5 is surface area. It's not area problem. You may have the area of a region as we did it before, but this is the area of a surface. Okay, surface area. See, we just recall what you did in calculus 2. You see in calculus 2, the question was, we call it solid after revolution over there. You see in calculus 2, a curve was given. You see this is a given curve. So this curve is, the function is going to be a continuous function. Okay, so this is going to be the curve in question, y equal to the f of x. Okay, and this is going to be the region in question. So what we do we just rotate this region. Okay, we rotate this region along the x-axis. Okay, if you rotate it along the x-axis, you are going to have a kind of a cylindrical shape here. We get a similar one down the here, and then this is almost going to be something. We get a cylindrical, okay, solid if you like. So if you take this one, we call it solid of revolution in those type of concepts. So if you pull this one out, you see if this is going to be your solid of a revolution, okay, or any three-dimensional solid. If we get the three-dimensional solid, then the one that you're going to call it the surface area is going to be if you go around this one. Okay, it's like, if you peel it off, if you like, if you have something like, you see, if this is going to be a kind of a solid that we have, so the surface area is going to be, okay, this one, for example, if you just go around, you see, this would be a kind of the result that you're going to have. It's going to be kind of, in this case, roughly, but these two portions are going to be kind of a curvy linear type. Okay, so if you consider that portion, that area that you are going to have, okay, if this is this, the radius is going to be, suppose the radius is going to be r, so you get a shape of a kind of okay, rectangular case if you like. And if this is going to be, let's call this one h, so we get the h over here. Okay, and this is coming from when you go around the circle here. So when you go around the circle, this height over here is going to be 2 pi r, circumference of the circle. So the area of this surface, if you like, area of the surface, just give you a rough idea, is going to be a kind of 2 pi r times h. Of course, you know that you partition it in calculus 2. You partition different parts, so each part would give you one of these, then you put them together, and eventually you have the area of a surface as this integral. Is going to be integral from a to b. Those area of the cross section is going to be 2 pi. Okay, that gives 2 pi for your okay. It gives you 2 pi, and this is going to be f of x. At when you do it, this is going to be, it's not going to be a straight line. You have to find this distance, and this distance is going to be, when it's a curvilinear one, and this distance is going to be what is going to be the arc length. So this is going to be the arc length of that arc, which is going to be 1 plus f prime of x all squared, and then the dx. So this is what we did for the function of one variable in calculus 2. Now we're going to see the extension of this one for a function of 2 variables. Okay, so I just recall this one just to refresh your memory. that would be useful for you to know what's going on. Recall that if if y equal to the f of x, of course it's going to be a positive continuous function is a positive continuous positive continuous function. If this is going to be the case on the closed interval of a comma b, then the area of a surface, then the area of the surface, surface obtained, of course, obtained by rotating or revolving, by rotating that region, and the curve y equal to the f of x when x is between a and the b. Reporting about the x-axis. Simply is given by this formula, the one that I put on the chart. So I write it down officially, and this is going to be the surface area. Is going to be integral from a to b, and that would be 2 pi. That would be 2 pi f of x, which is your function, and this is going to be 1 plus derivative of the function. I write it down in this form to be able to extend it, differential form, and the dx. You know that this is going to be the arc length. This is going to be the arc length that we have. So this is going to be the version of the function of one variable. Now we can create a function of two variables. When we get the function of two variables, then we cannot use the derivative. Instead of the derivative, as usual, we change it to the partial derivatives or differential. So these are going to be changed to the differential respect to the x and differential respect to the y. And of course, instead of the single integral, you are going to have a double integral to get it. So that would be an idea in order to make it official for a function of two variables, or a function of several variables in future. So in general, I'm going to extend that formula into the new version, two-dimensional version, function of two variables. So in general, a similar thing can be do the area. Now it makes sense because the graph of this type of function is surface. So in general, the area of the surface, the area of a surface is z equal to the f of x comma y. Where of course be focusing on the partial derivatives, they must be continuous. Where partial derivatives respect to the x and the y, partial derivatives f sub x and f sub y are going to be continuous. Are going to be continuous on the domain D, which is going to be a set in R2. If you have all this information, then we can do the similar thing over there and eventually arrive at the double integral. Are you done? So this is going to be the version that you have to memorize it as the surface area. Use it quite a lot at the end of the course. So this is one of the formulas that you have to have it. It's given by area of a surface. Area of a surface is going to be double integral on the domain D that you have to determine, but this is going to be the version. It's going to be the square root of partial derivative respect to the x at xy all squared plus partial derivative with respect to the y, x, y, all squared, and plus 1. Okay, it's going to be a double integral, so it's going to be dA. Depends on what type of region are going to have, type 1, type 2, then you can do it. This is one version. The other version is the same thing, but we can extend it for a function of 3 variables in future. So this is going to be the case. See the double integral. And you can write down in the notation of the partial derivatives, 1 plus round z round x all squared. Okay, plus round z round y all squared. Use both versions and the dA. So this is going to be the formula for the surface area. We are going to have one integral, we call it surface integral. To get that integral, you have to find this one first. And that integral is important, it's very interesting. All the animation of the Walt Disney's, okay, those movies, they're just using surface integral. And you will get it when we get to it, then we explain it for you. Okay, so for the time being, a function would be given to you, and they ask for the area of a surface or surface area. Okay, you write this formula carefully. You have to find this. The resultant integral is going to be double integral. Most of the time, you may have to use the polar coordinate to do it, because those surfaces are going to be symmetrically related to the cylinder, circles, semicircle, etc. Or otherwise, it can be done. Okay. So we give you a couple of examples to see how we're going to do it, and one of them would be given to you on this coming quiz. And I assign, I think you have 4 questions from this one that I assigned. Okay, any question? Make sure you have a correct formula. This would be a very crucial formula. Make a note, bring it, to this quiz. Of course, you need it for the next test and on the final. Usually give you one problem to find it. Okay, there are 2 groups of problems. I just give you the tricky one to explain it for you. And some of them are, of course, straightforward. But the one that I'm going to describe, the region is going to be descriptive region rather than giving you the region right away. Okay, so pay attention to these 2 examples. The one in your book, most of them are very easy, kind of a unique region, but you need to practice. Okay, let's see what's going to be the first one. The region like a triangular region, or in your book, rectangular region are popular. So I just give you one here so that you know how to handle it. So I would like to find the surface. Okay, find the surface area of the part. Okay, of the part of the surface the graph of this function, surface of z equal to, that's your function, z equal to the x squared plus 2y. Okay, you can use graphing calculator to graph it. That lies above. Okay, lies above the triangular region. Triangular region. Region T, this is where you want to integrate in XY coordinate, XY plane with the following vertices. The vertices are 0, 0, 1, 0, and 1, 1. This is where you want to integrate. You integrate on this domain, because this is your formula, and you have to, when you write your formula, it's going to be a double integral. As usual, you have to find the limit of integrations to see what's going to be the case. Okay, so identify this region to get a good idea of what is going to be that integral about. solution. Locate these vertices, okay, and then connect them together. Connect them together to get your region. Okay, this is it. So the points are going to be 0, 0. So this is going to be 0. Then you get 1 and 0. This is going to be 1 and 0. Then you get a 1, 1. So this is going to be 1. Okay, that's going to be 1, 1. And to make a triangle, and this is it, you add, you say this is going to be the line. Okay, this is going to be a line, and this is going to be the region that you have. Okay, this is going to be the triangle. Okay, so you're going to integrating on this region. Okay, integrating on this region. So identify your region. The way you're going to look into it, just because you have to find this integral, you have to decide what type of a region are going to consider for the limit of integrations. So if you keep the x between 0 and 1, going to the right, to the left, 0, 1, then for the y, you go to have, you have to go up and down. So up and down, you see up, down. Nice. Up, down, up, down. So down is y equal to the 0. This is y equal to the 0. The x-axis. Up is this line. And you know that this is going to be 0, 0, and this is 1. So this line is simply y equal to the x. Okay, the slope is 1. And you have, the point passing through 0, 0, and 1, 1. Even you can, it's clear that's y equal to the x. Any question? So the region that you are going to be selecting to integrating is going to be your x is going to be between 0 and 1. Okay, and your y going up and down. So y is going to be greater than 0, and it's going to be less than or equal to the x. Okay, this is going to be your region. Any question? So I just emphasize again that the T, the triangle, is a collection of points, x, comma, y, that satisfy this condition. X is between 0 and 1. Okay, and the y is between 0 and x. The one that I assigned for you, I think number 3 or 5 in your book, instead of triangle, you get the rectangle. That would be very easy because that rectangle is, it's just going to be a straight line, It's just two numbers, x between 0, 1, y between 0, 1. But this one, because it's a triangle, so you have to go through this y less than or equal to the x, okay? So identify the region, you know the formula, so you better find these partials first and then get your result, okay? Or you can write the formula and then bring the result. So the area of a surface is going to be the double integral on the triangle, okay? And the formula that we have. So we're going to use the 1 plus partial of the z respect to the x all squared plus a partial of the z respect to the y all squared and the dA. Okay, go and find these partials. Okay. So this is your z. So your z is x squared plus 2y. Okay, x squared plus 2y. So we're going to get the partial of the z respect to the x. So round the z round x is simply 2x. Okay, round z round the y is equal to 2. Okay, carefully differentiate, go back, substitute here to find your integral. So it's going to be surface area is going to be a double integral. Okay, the double integral here is going to be a square root of 1 plus a partial of the respect to the x, which is a 2x all squared. Okay, plus 2 all squared. Now, as you decided that you are going to have a type 1 region, okay, in type 1 region, so you go with the y first, your y going from 0 to x. Okay, then you end up with your x, which is going to be between 0 and 1. Okay, so the region that you have for the integration is type 1 region. Any question? And of course, here, this is going to be what? So we go with the dy first and the dx to integrate it. Any question? So simplify the inside and then integrate it. Okay, carefully integrate it. So what's going to be the inside? 2x squared will be 4x squared plus 4. So we have to simplify it a little bit. Are you done with this one? So I'm going to simplify inside the radical. Okay. And so we continue here. So we have the over a of s. Now simplify the inside the radical, so that'll give you 0 to 1. It's going to be 0 to x. Okay, so we did have a 2x squared, which make it to the 1 plus 4x squared, and the 2 squared is 4. And then there is a dy dx. So 4 and 1 would be 5. So that give an integral from 0 to 1, 0 to x. Okay, 0 to x, and this would be 5 plus 4x squared. Okay, the dy and the dx. Now we're integrating. We have to integrate respect to the y first. See, respect to the y. This would be just a constant. So integral would be just a y. So it's going to be 0 to 1. Okay, y 5 plus 4x squared as a number, but your y going from 0 to x. And when you're done, you come back and you integrate respect to the x. Any question? Now replace the y by x and the 0, so that give you 0 to 1. Okay, 0 to 1, if you substitute y equal to the x, that give you x radical 5 plus 4x squared, and replace 0, that give you 0, the dx. Okay, you have to find this integral. You know that you have to change it and use the u substitution. So that give x times 5 plus 4x squared to the 1/2 and the dx. Okay, you can do your substitution in short form or in general. So this is it. You are going to call this one u. So u would be 5 plus 4x squared. So your du would be 8x dx. So I need the 8 here to replace everything by du. So what I do, I need the 8, so I divide by 8. It's the way you do it. I do it in short form. You can substitute if you like. It's going to be 8x times 5 plus 4x squared to the 1/2 dx. Okay, so over here I have everything I need. So this is going to be like u squared, and the integral would be u to the 3/2 over the 3/2 is going to be 2/3 of the u to the 3/2. So this is going to be 1/8 5 plus 4x squared. Okay, to the 3/2. Okay, to the 3/2. 2/3, of course. So I write 2/3 here. And then going from 0 to 1. Any question? So it's a u substitution. You can do it if you like, let's go back and substitute. But I do it in the short form. I need the 8 here, so I multiply by 8, divide by 8. So that would be simply u to the 1/2. So u to the 1/2 would be u to the 3/2 divided by 3/2, which is a 2/3. Okay, now I simplify this one first, and then I substitute. So that would give me 4 times 3, 12. So I have 112 times 5 plus 4x squared to the 3/2 to be evaluated from 0 to 1. You substitute if you put x equal to 1. Okay, if you put x equal to 1, so that gives you 112 times 5 plus 4 minus 112 times 5. That's to the 3/2. and that would be 5 plus 0 to the 3half. Okay, 5 and 4 would be 9, so that give me 112, 9 to the 3/2. Okay, minus 112, and this would be just 5 to the 3half. You can use your calculator if you like to get these numbers, but if you don't, you just simplify it a little bit, and then you're done. Some people use calculator. If you don't want to use calculator, 9 to the 1/2 would be 3, 3 squared, 3 cubed would be 27. So that give you 27. Okay, and that give you just a negative 112. You can't do anything about this one. Okay. It's going to be, it's a 5 to the third would be 125. Radical 125 would be 5 radical 5. Okay, so that gives you 5 radical 5. Okay, so it's going to be without calculator. It's going to be 12, and that would be 27 minus 5 radical 5. So this is going to be the area of a surface. It's up to you if you want to use your calculator and estimate it. But otherwise, we accept it. Okay, so the area of a surface, 27 minus 5 radical 5 over 12. As you can see, the integral, it's just got more involved. Okay, it's just like finding a double integral, really. Okay, when you put them together. So that's why they are popular. Okay, and we have to practice, make sure that we are ready for it. Any question? So make sure that I've seen some people miss the formula. Make sure you bring a correct formula, and then there is going to be a radical expression that you have to decide. You'll say this radical, and most of the time it's going to be U substitution, and the other version is going to be the version of the that we do the polar coordinate when we see the chance. So I give you one more. Any question? This next problem is very popular. So there is a techniques that we are going to use in some other places as well. I've given this type several times on the test, and some people, they miss it. So there is going to be idea of, you see, this is one curve. The region that you got is just the area of one surface, if you like. But in the cases that we're going to have, you may have like in calculus 2. You may rotate the region between two curves. Remember, if you have two curves, the intersection of the curves would create a region. Then you rotate that region along the x-axis or y-axis, and then you create the volume and the area of a surface. It's going to be the same thing for this. So that's what the people, they miss when it's going to be two different curves or two different surfaces. Okay, and the most popular problem is this next one. We're going to use it in different contexts over there. There is one form for the polar coordinates. We are going to do it tomorrow when we get to those practice one. So pay attention to these type of problems. Okay, from now on, you will see it from time to time. So it's kind of area between two surfaces, that area that you are going to be interested in, to find the surface area of that, okay? And so we would like to find the area. Okay, the area of a part of the surface is a paraboloid of the paraboloid. Well, the paraboloid is z equal to the x squared plus y squared. So that's going to be a paraboloid. Because if you pick the z constant, the cross section is going to be a circle. Cross section is going to be a circle, but it's like a cup, if you like, a cup of coffee or something. So this is going to be the area of a part of the paraboloid that lies, you see, that's it, that lies lies under the plane. The plane z equal to the 9. So you have two different, two surfaces, if you like. So this is going to be the 1, and the other one is z equal to the 9. Okay, roughly, again, you can use a calculator or just graph it into softwares that will show you. Roughly, this is, this is what would happen really. So the situation they're going to have, and this is the one that we talk about it, a kind of a paraboloid. So it's going to be a parabola. Then the cross section is going to be a kind of a circle. Okay, this is it. It's going to be a paraboloid over here. And then you have that z equal to the 9, which is going to be a plane. Okay, somewhere here. Okay, the important part for the, okay, as you can see, because when you want to integrate it in the double integral, you have to project this one into the, into the xy coordinate, if you like. If you project it, this top one would be like a circle. Okay, this is going to be the one that you have, and there is going to be the plane somewhere. Okay, z equal to the 9. You have that plane, so this is going to be x, y, z. Okay, so in between, you are going to get that area, that surface area that we're going to be interested in. So if you project it into two-dimensional, if you like, if you project it in two-dimensional, this is a situation you're going to have. You see, z is equal to the x squared plus y squared is one of your, one of your graph. If it was by itself, you replace z by 0, that gives you the projection. You shrink it, you drop it down into the xy coordinate. But it's not. You have an area between two surface, and you have a z equal to the 9. So if you want to know what would happen in two-dimensional, you have to find the intersection of these two together. Okay, if you intersect it together, so that gives you x squared plus y squared equal to the 9. So when you shrink it, when you drop it, when you project it into the two-dimensional, the case is going to be something like this, if you like, it's going to be a circle here. It's going to be a circle here. So the domain that you're going to integrate for us, remember the D subset of R2 are going to be a collection of points, X and the Y, that satisfy this condition, X squared plus Y squared equal to the, equal to the 9. So it's going to be a point on the, a point on the circle. This is going to be 3, this is a -3, and up and down. So this is going to be the domain that you're going to have. Okay, so this is the one that some people, they missed it. You are going to be given, when you see 2z in this problem from now on, get the intersection, because even with the triple integral, then you have to go to the double. You have to project it, drop it down into the plane. Then when you drop it down into the plane, it's going to be two variables. Then you can do your integration that you have. Okay, so don't miss it. You have one in your book, and I just put one very similar one in that practice one that we have. And we're going to see it again. This is z equal to the 9. You may have something else over here. Okay, you may have, x squared minus y squared, etc. Then you can intersect it to get these results. Okay, so this is it. And now we know what to do. Surface area. Now the surface area is double integral on this domain. On this domain, and the function is 1 plus, round z, round x, all squared, round z, round y, all squared. Okay, and your dA. Go and bring these dc dx that you are going to have. Okay, of course, your function. So the situation you're going to have is going to be So we get the z equal to the x squared. This is it. Z is equal to the x squared plus y squared. So you find the dz dx, which is a 2x. And you find the dz dy, which is going to be a 2y. So substitute here. So it's going to be as the double integral. Stay with the d to see what's happening and decide how we're going to integrate it. So this is going to be 1 plus 2x squared. Okay, 2y squared and the dA. So if you do this, it's going to be integral. Let's see, it's going to be 1 plus 4x squared, 4y squared, and the dA. You see, if you factor out the 4, so this is it. You have to include 1 plus 4 times x squared plus y squared dA. Now look at this one. What is your d? Your d is a circle. Your d is a circle, and you want to find this integral on the circle, and you will see x squared plus y squared. So you better do the polar coordinates. You see, automatically, you realize that you have to use the polar coordinate to get this integral, because you have the x squared plus y squared over here, and the d is going to be just a circle. So you have to change it to the polar form. So go back to your circle to get the situation that you have for this. You see, this is your circle. This is going to be your circle. The radius, remember, the radius was 3. So in the polar coordinate, this means your r is going to be between 0 and 3. And your data is a full circle, is going to be between 0 and 2 pi. Okay, so I'm going to change this integral from the rectangular one to the coordinate, and then we do the polar form, then I'll be able to do it. Okay, are you ready? In the polar form, remember, this would be what? This would be integral of polar form. R going from 0 to 3, 0 to 3. Data going from 0 to 2 pi, 0 to 2 pi. Function 1 plus 4. Remember, x squared plus y squared is r squared, so that gives 4r squared. But in polar form, remember, there was an extra r, Jacobian. Extra r, dr, d data. So you have to realize it yourself. It's very typical problem that, you see that you have no other choice. Easily seen that you have to use the polar coordinate because the domain is a circle. Domain is a circle, and the expression is nicely symmetric. Okay, any question? If you change this one into the, 1 plus 4r squared to the 1/2, your substitution will do it right away for you. Because the derivative of 1 plus 4r squared would be just 8r. You already got the r. So you need an 8 like the one that I did. You can simplify it and just go ahead. Okay, so I'm going to rewrite this one to the 1 plus 4r squared. Any question? So I told you, this is a very typical problem that, you get quite a lot from this. Okay, you learn it for the other parts, and it's going to be used in various format. So this is it. I continue. I'm going to rewrite that radical. So I have the integral of 0 to 2 pi, 0 to 3. Okay, now I change it into the r times 1 plus 4r squared to the 1/2. Then the dr and the d data. Again, use substitution. I take this one to be u. So I remind myself, if I take u to be, again, I do it in the short form, but you can do it yourself, whatever you like. I remind myself that if u is going to be 4r squared, my du would be 8r dr. So I need the 8 here. So what I'm going to do, I'm going to create the 1/8 outside. Then I'll be able to write this one by 8. So I have the dr. Okay, I have the du. And that would be 1 plus 4r squared to the 1/2 dr. Okay, I'm sorry, I missed the 0 to, this is 0 to 3. Okay, and then when I'm done, I'm coming back and take the respect to the data. So you see, this is going to be my u, and this is going to be my u prime, or the dr that I need. So I end up with the integral of u to the 1/2 du, which is going to be u to the 3/2, 2/3 of the u to the 3/2. So I can go on. It's going to be 1/8, 0 to 2 pi. I integrate this one. I can do it, so that you can see it. 1 plus 4r squared to the 3/2 over the 3/2. Then r going from 0 to 3. Then when I'm done, I'm going to take the d data. As soon as you provide the u prime, okay, provide the du, then you can use the Popper rule, to get this one through. Now divide by 3/2 is going to be 2/3 up. So it's going to be 1/8, 0 to 2 pi. And this is going to be 2/3 times 1 plus 4r squared to the 3/2 from r equal to the 0 to 3, and then the d data. Okay, you may have to use your calculator or just evaluate it. So what's going to be the result? We are going to substitute r equal to 3, and this is a 2/3. You can pull it out. You see 2/3, you can simplify this as a 4. So 3 times 4 would be 12. So that gives you 1/12. Integral from 0 to 2 pi. Substitute r equal to 3 first. So it's going to be 1 plus 4 times, I write it down, you know what's going on. It's a 3 squared, everything to the 3/2, minus r equal to the 0. R equal to 0, that gives you just 1, 1 plus 0 if you like, to the 3/2. When we're done, we come back and we make it the data. So 3 squared would be 9, 9 times 4 would be 36, 37. So it's going to be 1/12, integral from 0 to 2 pi. Okay, 37 to the 3/2, and that's going to give you 1, minus 1. Okay, the d data. You can pull it out and then decide what you want to do about it. Okay, so this is it. It's going to be, if you like, 37 radical 37 minus 1 over 12, integral from 0 to 2 pi d data. So we know that this would be data 2 pi. It's going to be 37 root 37 minus 1 over 12. And that's the data from 0 to 2 pi. So it's going to be 37 radical 37 minus 1 over 12 times the 2 pi. So 2 and the 12 would be simplified. So eventually the area of a surface is going to be something like pi 6 times that by 37 radical 37 minus 1. Okay, so don't be surprised if you see this type of combinations when you do the surface area. Okay, it's a nice application of the double integral. Really, that's the one that we are going to be interested in. But as I told you, we are going to come back to it when we get to the chapter 15. I'm not going to do anything about it now, but we are going to see it. The last type of integrations that we're going to introduce at the end of the course. Okay, so this is the surface integral. So this is where we give you the quiz. Okay, we give you the quiz after this one because we finish everything about the double integral. The other thing that we have to do in this chapter is triple integral. The definition of the triple integral, because you already done the double, it's almost the same. So you are going to have an extra integral, and that integral, it's a dx dy, is going to be x, y, and z. almost everything can be nicely extended. The only difference is when you want to evaluate it. The usual practice are all nice, but when you look into the version like similar to the polar coordinate, that would take time to do it. And that's why I want to give you just a definition of triple integral today. We are not going to give you any question on the quiz or any assignment, so that we get enough time to practice cylindrical coordinate and spherical coordinate next week. We have three concepts to check with the triple integral. You have that cylindrical coordinate. We have to introduce cylindrical coordinates and work on it. A spherical coordinate, and there is one argument about remember the substitution method in calculus 2 or calculus 1, U substitution. That the substitution method can be extended to the function of several variables. And that's quite interesting. Sometimes in calculus 3, some people, they avoid this one, or in some books, they consider the cylindrical coordinate and a spherical one and the polar coordinate as of the substitution method, but it need to be talking about, because if you are measuring physics in future or something related to that, you are going to use this type of idea. That's why we are going to cover it. So that would be 3 sections for the next week. So that's why I'm going to do the triple integral now, okay? And then tomorrow we can practice, even we may start practicing today, okay? So triple integral, it's the same. Remember, we defined the double integral on on a rectangle, because there are 2 variables. Now when we make a triple, your function is a function of 3 variables. Instead of a rectangle, you are going to have a box. So you integrate respect to the box, and the same thing, you are going to use the iterated integrals. You freeze 2 variables and integrate respect to the other one. You can freeze the x and the y, integrate respect to the z, then come back integrate respect to the y, integrate respect to the x. Okay, it's just those preliminary parts are easy to be done. But in science, you are going to use the triple integral for the main application. Okay, so this is going to be 16.6 that we are going to cover. I covered 3 sections of this. This is a 6, then I do the change of variable and a substitution method. I finish this chapter right on time for the test 3. When we get to quiz 4, everything is new. We can forget about whatever we did, because we introduce a new type of function from physics, and then we give it the last type of integrations, and then we are done. Okay, so what is triple integral? That's it, triple integrals. Everything we talked about it before are going to be extended. So we do it briefly. We need a function, but the function of 3 variables, and we need a box. So if a function, I copy whatever we did before. If a function, 3 variables, f of x, y, z. Okay, of course, it's continuous. Is going to be continuous. You need a continuity to guarantee that the integrals exist. Okay, if a function f x by z is going to be continuous over, now is going to be the rectangular box, like a cube. Rectangular box, usually denoted by Q. You see, it's going to be, you need 3 close interval. 1 for the A, 1 for the B, 1 for the X, 1 for the Y, 1 for the Z. So the first one is A comma B cross. This means X is between A and B. C comma D. This means Y is between C and D. Cross. Let's say we go with the K and L. This means z is between these. Okay, x, y, z. So if your function is going to be continuous on this box, then we can define the triple integral. Then just by those iterated formula. Then the triple integral of f over this box over q is defined by, this is it as we did it before. So this is the way we write it down. 1, 2, 3 q triple function f of x, y, z. And instead of those dx, dy, dz, we write dv, differential of the volume. Differential of the volume would be dx times dy times dc. And is defined as we did it before. That's it. 1, 2, 3. A to b. This is for the x. C to d. This is for the y. K to L. This is for the z. So the function is going to be f of x, y, z. Okay, now. So we integrate, and that's it. So what we do, this is a, b, c, d. So we go with we integrating. The z is here, so it's going to be dz. You can go with the dx, dy, z. It doesn't matter because we can change the order. But as I write it down over here, so this is going to be, I integrate respect to the dz first, then I go with the dy, then I go with the dx, or I can do it the other way around. Okay, so is defined by this one. You can, as we did it before, is a limit of those partial sums. So it's going to be something like, we call it xi star, yi star, zi star, and then this is going to be delta vi star. We just slice it into different parts, that region and region. It's just interpretation as we did it for the other one. But we know that as soon as you freeze the two variables, it's going to be iterated integral. If you want to get the geometrical interpretation of this one, it depends on the application. The only thing that you can do is if you consider this function, if you replace this one by identity function 1, if you replace it by 1, then the triple integral would be considered as the volume. Otherwise, you can't do anything else. Okay, so we just emphasize that, note that. So if you want to do the volume problem by the triple integral, you have to replace this one by 1. Okay, so that's it. Note that the volume, okay, the volume of the solid, okay, the box of the solid Q is going to be given by, solid Q is going to be given by, this is it, the volume of Q is going to be a triple integral over Q of the dV. We usually do the volume problem using the double integral. If you want to use a triple integral, you have to replace that function by 1, because that gives you simply dx, dy, dz, and you'll be able to do it. Okay, so since we already done the double integral and the argument that we did have, Frobenius theorem, iterated integral, all of them are extendable, if you like. So we have nothing to worry about. The only thing is, again, you have two types of integrations. The type that the limit of integral, everything would be given to you, that's fine. The only one is the descriptive one. You know that these are not going to be numbers all the time. You may have a kind of curvilinear region. The way you look into it, we usually freeze the z Then we drop the function in two-dimensional. When it's going to be a two-dimensional, this part is going to be a double integral. So whatever you did before, it's going to be valid for this one. Okay, so this is the way we are going to operate regarding this integral. Otherwise, that's all we can do. Okay, so let's give you one of them. So it's a straightforward. You got to be patient to take through this integral. Make sure you know this definition. X, Y, Z. Sometimes they give you this one right away. You should be able to read it. Okay, let's get a standard one to start with. Let me just give you a couple of examples. We don't have anything else to do. So I'm going to go to the next page because we need more room. Those triple, you can do them at the same time, or you can do it one by one outside. Example, one version. On the test 3, you will see one of them. And on the final. Okay, evaluate the triple integral. It's going to be a straightforward one. Evaluate the triple integral. You get 3 questions on the final from the triple integral. That's it. 1, 2, 3 over the cube. And the function is 12x y squared z cubed dv over the cube, where the q is there. Q is equal to, okay, what's going to be q? Close interval of -1 and 2. This means x is between -1 and 2. Cross 0 and 3. This is the limits for the y. Cross 0 and 2. Okay, so you must know it yourself that this is x, this is y, this is z. Because you have to rewrite this one. Okay, solution. So rewrite it 1, 2, 3. And 1, 2, 3, 12 x y squared z cubed dy dv. When it's a number, you can do it in any order. It doesn't matter. Okay. I'll go with the z first. So z is between 0 to z. Then I go with the y, 0 to 3. Eventually x, -1 and 2. So the order that I pick is this one. I go with the z first, dz, dy, dx. Or you can switch the order, but make sure that you put the correct limit of integrations. Any question? Start integrating. You integrate respect to the z first. So it's going to be -1 to 2, 0 to 3. Z. That gives z to the 4th over 4. Again, you can do it separately. I do it all together, 12x y squared. Okay, z to the 4th over 4. Then emphasize that the z goes from 0 to 2. Okay, and when you're done, then you continue with the dy dx. Substitute for z, that give you 2 to the 16. Okay, you can simplify it. So I explain it, but you can do it right away. So 2 to the 4 is going to be 12x y squared, 2 to the 4th over 4, minus 0. Okay, then the dy dx. 2 to the 4th would be 16. 16 over 4 would be 4. 4 times 12 would be 40. 48. Okay, 2 to the 4th would be 16. 16 divided by 4, and that give you 4. Then I multiply by 4 and just make sure, yeah, I get the right answer. Okay, that was 2 to the 4th, 16. Yeah, I think it's going to 48 is correct. Yeah. So it's going to be -1 to 2, 0 to 3. Okay, so I have the 48 x, okay, x y squared dy dx. Okay, I substitute 2 to the 4th, I then simplify it. 2 to the 4th, 16. 16 divided by 4 would be 4. 4 times 12 would be 48. Okay, now integrate respect to the y down. It's going to be -1 to 2. Respect to the y, 48 x y cubed divided by 3. So y going from 0 to 3, then the dx. Okay, simplified substitute, we can simplify that, give us 16. So that give a -1 to 2, 16x y cubed. Now y from 0 to 3, then the dx. If you substitute 3, so we're going to get what is a -1 to 2. So it's going to be 16x 3 cubed minus 0, then the dx. 3 cubed would be, okay, 27 times 16. So it's going to be -1 to 2. Okay, and that is 27 times 16 is going to be, I think it's a 432. It's a 432x. Okay, x dx. Okay, now we get the time to integrate respect to the x. So that gives a 432x squared over 2 from -1 to 2. You can simplify it by 2. So by 2, that gives you 2, 1, 6 x squared from -1 to 2. Now substitute these two numbers to get the final answer. So eventually this is going to be 216. Okay, 216, 2 squared minus 216. Okay, 2 squared would be 4. So this is going to be 216 times 4 minus 216, which is going to be 216 times 3, or your calculator right away. So the final answer, 648. So that gives you the result of the integration. Again, it's not difficult. It takes times, and you got to be careful when you write it down. Usually, one of them would be given. There are 2 groups. This is the first group. Okay, so I give you a break. We come back and we do a couple more. The descriptive one is the one that you've got to be careful to be able to take care of it. Okay, 11:55. Let's come back around 12:10. Then I do a couple of them, and then we go to the bigger time to start looking at some of the problem of the practice, that practice quiz. We put them together. Okay, see you then. Okay, we are going to continue. This one, exponential one, is very popular. So I'll give you one more of this abstract form. Okay, so we want to integrate this function. Just to show you that the limit of the integrations can be also function, non-rectangular region, as you did it for the function of 2 variables. Okay, so this is going to be the example, and you want to evaluate this integral. So evaluate, the integral is this. Triple integral, 1 to 3, okay, x to x squared, and 0 to ln x. Function x e to the y dy dz dx. You see, that's your integral. It doesn't matter. You see the limit of integration. We can have a non-rectangular region or the curvilinear region. So the order is important. You integrate respect to the y first. Integrate respect to the y, you're just integrating e to the y. Integral of e to the y is just e to the y. Okay, so this is how we're going to handle it. Solution. I'm going to call it I. So this is how I'm going to start. I start with the y. So I rewrite it. So 1 to 3. You can do it, right away, but I explain. So I do this part first. 0 to ln x. Okay, the function is x e to the y, integrate respect to the y. And then I go with the z and the x. We talk about it, the integral respect to the y with just e to the y, x, so nothing would change. 1 to 3, x to the x squared. This would be simply x e to the y, but y going from 0 to ln x. Ln x, okay. And when we are done, then we integrate respect to the z and the x. Now substitute is going to be 1 to 3, x to the x squared. You start y equal to the ln x, so that gives x e to the ln x minus, if you replace y by 0, that gives x e to the 0. Then dz dx. Okay, carefully substitute. E to the ln x would be x. You know that e and the ln function, they are inverse of each other. So that takes you back to the x, and e to the 0 is 1. So you are going to get 1 to 3 x to x squared. Now the leftover is going to be, you get the x here, x times x. You see we get x times x would be x squared. So that's going to be x squared. Okay, minus x, and now the dz dx. Okay, any question? Now the next step, the next step we integrate respect to the z. Would be just z. This would be constant. So it's going to be 1 to 3. So you're going to have x squared minus x. Okay, you get the x squared minus x. The integral is just z. Okay, but z going from x to x squared. And when we're done, we come back and integrate respect to the x. So replace z by x squared and x. So it's going to be 1 to 3. X squared minus x times z x squared minus x squared minus x times z, which is x. Okay, then everything dx. Okay. Now you have to simplify, but then integrate it, multiply. That give you 1 to 3. You multiply inside. That give you x to the 4th minus x to the 3rd. That would be minus x to the 3rd plus x squared. okay, the dx. Combine the like terms, it's going to be 1 to 3, and you get the x to the fourth, that give you minus 2x cubed plus x squared dx. Okay, so this is going to be the resulted function. Now we integrate with respect to the x, and we substitute. So this is going to be x to the fifth, x to the fifth over 5, minus 2x to the fourth over 2, plus x to the third over 3. Then you evaluate from 1 to 3. Okay, we can simplify it. So that gives x to the fifth, 2x to the fourth, this must be 4. Okay, x to the fourth over 4. So I simplify these two. So that gives me x to the fifth over 5 minus x to the fourth over 2 plus x to the third over 3. Then I have to find it from 1 to 3. Now we can substitute x equal to 3 and equal to 1. So it's going to be equal to the, put x equal to 3, plug in 3 to the fifth over 5 minus 3 to the fourth over 2 plus 3 cubed over 3 minus, replace x by 1, so that give it a fifth minus half plus 1/3. Okay, simplified and then be done. 3 to the fifth, 3 to the fourth, 81, 243, and okay, that give you 243, 243 over 5, and that give you 81 over 2, and this is going to be 27 over 3. Okay, apply the negative sign, a fifth plus 1/2 and the negative 1/3. You can find the common denominator all together, or just simplify it a little bit and do the job. Okay, these two, for example, that's a 243 minus 1, that give you 242 over 5. So this is how I simplify these two. So I do this one, a negative 81, and the positive 1, that give me negative. Okay, so that give me negative 80 over 2. Okay, negative 80 over 2 is going to be minus 80 over 2. And finally, I have 27/3 minus 1/3. It's going to be 26. So it's going to be plus 26 over 3. Okay, then you can find the common denominator, which is going to be 30, and then do the job. Okay, it's going to be 30, common denominator, 30 divided by 5, 6. 6 times 1152. Okay, and that gives 15 times 80 is going to be 1200. And that gives you 260. Okay, that gives you 10 minus 260. That was 27. And this is a negative. Didn't make any mistake here. It is a negative sign, so they give a negative 3 here. Okay, negative 1/3. And that is 27 minus, okay, it seems to be fine, except this one. That's a negative 2/3 and the x squared. I just not sure about that sign, but it seems to be all right because I get a positive one. But anyway, you can check it. So that give you 260. Okay, just put these together and get the result. So okay, check the top. I can see it's going to be 3, maybe 20, maybe 28. Just you have to check it. Okay, So that gives you the final. There was a sign here that I felt that I missed it, but I don't think so. Because there is a negative here and negative is positive. So this is correct. Then this is also correct. So it seems to be fine to get these numbers. So just be careful, these type of ideas, e to the ln x that give you x. And when it's an exponential one, pay a little bit more attention. Okay, this is type 1 problem that when you evaluate the triple integral. There is going to be another type, which is they describe the region. Then you have to set up the integral yourself. Okay, just give a couple of examples of that one too. Any question? So as you can see, it's like the double integral, but you have an extra parts. The descriptive one is quite interesting. That give you a better idea, even help you for the double integral. They describe the region, then you put them together. Okay, there you are. Example. What is this region? You have a region that's described by the following. Suppose the solid that you are going to integrate on it, Q is a solid. Is a solid that's described, bonded. Okay, bonded by the planes x plus y plus z equal to 1. That's one plane. Z equal to the 0. You drop into the xy coordinate, x equal to the 0, and the y equal to the 0. Okay, coordinate planes. Now, what they would like you to do is they would like you to evaluate this integral. Triple x dv on this Q. You see, this is descriptive problem. So you have to find the limit of integration yourself for these problems. The way we are going to do it, we look for the z first. You just check to see how many z's are you given. You see, this is one. You have two planes. One of them is this one, and the other one is z equal to 0. So the way you do it, you just solve for z, whatever you have. So this is already z equal to 0 is already solved for z. You solve this one for z. That gives you z equal to the 1 minus x minus y. So your z is going to be between these two values. So that gives you the range for the z. Okay. So you look into the problem to see the equation, the information that given to you in terms of the z, you collect them. So you collect this information that, you get the z equal to the 0, 1 plane, and the other z is coming from here. You solve for z, that give you 1 minus x minus y. So your z is going to be between these two numbers. That's your z. Then you have to drop it down into the two-dimensional, whatever you have. Drop it down means you project it. You project it, projection, to project this one, you replace the z by 0. Or if you have two z's, you just find the intersection of these two. You see z equal to 0 is 1, z equal to the 1 minus x minus y. The intersection would be when you put the z equal to the 0. So you replace the z by 0, there is no z. So you are going to be down into xy coordinate. When we get to the xy coordinate, it's a double integral. So in xy coordinate, you have x plus y equal to the 1, which is a straight line, and you have the intercepts. So you identify what type of region do you have in two-dimensional. You may have the type 1 or you may have the type 2, and you take care of the integral of that part. Okay, this is the way you are going to do it. And that's your, your challenge, if you like. we practice and we can do it. So the solution is going to be, first look for the z's. I can see the z in two places here. So I note that I have two places for the z. I have the x plus y plus a z equal to 1, and I have the z equal to the 0. Okay, if I put them together, I find the z from here. So that gives me z equal to the 1 minus x minus y, and I have z equal to the 0. So now I get the range for the z. So my z must be greater than equal to the 0, and it must be less than equal to the 1 minus x minus y, between those two planes that we're going to have. This is going to be the limit for the z. Any question? Now for the x and the y. Drop this one down into the two-dimensional. Replace by 0, so we call it the projection. Shrinking. The projection of Q, that's solid, onto, okay, on the xy plane, or onto xy coordinate. If you drop it down, so this means you replace the z by 0. So dropping down, that gives you this equation. Equation is x plus y plus 0 equal to the 1. So the result in two-dimensional is this one. Is this and the information that you already got. So in two-dimensional, you are going to end up with the x plus y equal to the 1, and you have the x equal to the 0, and you have the y equal to the 0. You know what it is. If you graph it, you see. So these are going to be just give you the intercepts. You see, if you replace the x by 0, in this equation, x by 0, y would be 1. If we replace y by 0, that gives you x equal to 1. So what's going to be the graph that you are going to have? These are the intercepts. So 1, x, 1, y. So this is going to be the line. So the region are going to be the one that's going to be bounded, enclosed by the line. This is going to be your line. Okay, if you like to solve it for y, that give you what? That give you 1 minus x. This is the line, and this is going to be the region. This is going to be the Q in two-dimensional. So in two-dimensional, again, the same argument that we did before. Are you going to consider this one as a region, okay, type 1 or type 2? Just check. For the x, you go to the right to the left. Right to the left, your x would be between 0 and 1. For the y, you have to go up and down during this region. You see, up, down, up, down, up, down, up, down. So up, down means your y would be between the x-axis, which is y equal to the 0, and it's going to be always below the line. And the line is y equal to the y minus x. So that gives you the domain or all the restriction that you need. So the region that you're going to pick for the integrating the double integral is going to be type 1. So type 1 region. This is the way you are going to handle the type 2 of this information that are going to be given. Okay. So this part is like the double integral that you did before. If you just forget about the first part, is exactly kind of similar to the tetrahedron that we did before. So you have to look for the z's, those values that's coming to you to get the restriction for your z. Then you project it into xy coordinate, replace it by 0. You are going to be in two-dimensional. When you're going to be in two-dimensional, it's going to be one of these regions that you did before. It's a kind of a triangular one here, so just pick the. So now we are ready to set up the integral and to get the result. Okay, any question? So this is the part that we're going to practice. So there you are. It's going to be a double integral. Triple integral. Z goes from 0 to 1 minus x minus y. Then you have to integrate respect to the y, because y is between 0 and 1 minus x. And at the end, you integrate respect to the x. Okay, I write it down here. Then I do it. So, and that's it. We say that the triple integral, it's given to us. X dv is going to be equal to this 1, 2, 3. The function, it's x dz dy dx. Okay, this is the one we pick. So over z is between 0 and 1 minus x minus y. Then we do the y between 0 and 1 minus x. And at the end, we do the x, which is 0, 1. Okay, so this is how we're going to set up the integral. The integral is usually easy integral, but those domain are important. So the integrate respect to the z, that would just z, xz. So it's going to be equal to the 0 to 1. Okay, 0 to 1, 0 to 1 minus x. Now we have xz, and z going from 0 to 1 minus x minus y. And when we're done, we come back and integrate respect to the y and then respect to the x. Any question? It's easy, you know, if you press 0, you get nothing. Replace z by 1 minus x minus y. So that gives integral from 0 to 1, integral from 0 to 1 minus x, simply x times 1 minus x minus y. You know that the rest is going to be 0. And you are integrating this one respect to the y first and then the x. 0 would be nothing, so you have to multiply this inside to be able to integrate respect to the y and then respect to the x. Any question? I have to go to the next page to continue. So multiply this one, x minus x squared minus xy, dy dx. So I continue. So I call it I and continue. So integral now is going to be 0 to 1, 0 to 1 minus x. And if you multiply them together, that gives x minus x squared minus xy. To be integrated respect to the y first, then respect to the x. Okay, continue, integrate respect to the y. That would be xy, negative x squared y. That would be negative x, y squared over 2. So 0 to 1. Xy, x squared y minus x, y squared over y. Okay, and everything going, see everything here. Then y goes from 0 to 1 minus x. And then we done, we get the dx. Carefully substitute. If you put the y equal to 0, we get nothing. So we put the y equal to 1 minus x carefully. So it will be 0 to 1, x times 1 minus x minus x squared times y 1 minus x minus x times 1 minus x all squared divided by 2. Okay, and everything is going to be dx. Okay, you know, you can do a little bit of algebra if you're going to be interested in, or eventually you have to multiply it. See, you can factor out 1 minus x first, then simplify it. But it's not a big deal. Depends what you want to do. I'm going to multiply it because eventually you have to multiply. But if you factor it, then you can use U substitution to integrate it. Okay, so I'm going to multiply it. This is it. Carefully multiply 0 to 1. So that gives x minus x squared, the first one, minus x squared plus x cubed And on the top is going to be negative x times, you have to square this one first, 1 minus 2x plus x squared divided by 2. Okay, then everything dx. Combine to the like terms, simplify further. Okay, 0 to 1. So what you can do so far is going to be x squared and x squared minus 2x squared plus x cubed. We have to multiply the top by x first. That gives x minus 2x squared plus x cubed over 2. Then the dx, you have to find a kind of common denominator or just, okay, look that bracket, it depends which one do you prefer. So if you put the 2 here, so it's going to be 2 times 2x minus 4x squared plus 2x cubed. Apply this negative sign to everything on the top, negative x plus 2x squared minus x cubed dx. Okay, combine the like terms. You can pull out the 1/2. Integral from 0 to 1. So on the top, we have a 2x and minus x. That gives us an x. Okay, this is a 2x minus the minus x will give you x. That's it. Then for the x squared, negative 4x squared and a positive 2, that give you negative 2x squared. And for the cube, 2x cubed minus cube would be x cubed. So that's it. You integrate it respect to the x, and you are going to have an x squared over 2 minus 2x cubed over 3, and the plus x to the 4 over 4 from 0 to 1. If you put the 0, you get nothing. If you put the 1, that should give you the final answer. It's going to be 1/2 times 1/2 minus 2/3 plus 1/4. Okay, get the common denominator inside. So it's going to be 1/2. And the common denominator would be 12. 12 divided by 2, that gives 6. 12 divided by 3, 4. 4 times 2, 8. And that gives you 3. So the top 9 minus 8 would be 1. So 1/2 times 1/12. 9. So I have, I didn't miss any signs here. This is going to be just a double check that I think everything's all right. I get the 1/2 here, x to the 4th over 4. So I get the 1/2 negative 2/3 plus 1/4. Then I pick the common denominator. So that is going to be the case. The common denominator is going to be 12. 12 divided by 2 is 6. That give you 4, 8, and 3. It's all right. So that's going to be 9. So I have 1/2 times 1/12. I think that would be 1/24. The final answer. Okay, so that region, that starting point was important one to be able to take care of it. Any question? So it's going to be of this type of nature, this integral triple one. There are other formats that's going to be because it's a triple integral, the function of 3 variables. You may see something like those cross section quadratic form that we have, ellipsoid, but in that form we need those techniques similar to the polar coordinate, which is going to be a spherical one and cylindrical. That's the 2 sections that I talk about it, that we have to do it next week. So this is it. I'll give you one more that I have. It's very similar, but it's kind of a trigonometric one. And then that's it. And this is about the triple integrals that we have to just change it first. We need those 2 different systems that we do next week. Okay, let's just give you one more. This is also important. So as you can see, it's It's just one more step. It's all double integral is the one that's going to be important. Okay, let's check this one too. Example, again, a descriptive one. As I told you, we can have only this type at the moment. The second group for next week. Okay, there you are. Suppose Q again, the solid is going to be a solid, okay, a solid bonded by. The planes are a little bit different, but it's the same. Q is a solid bonded by the plane this time. You see the planes? It's a little bit a straightforward one. The plane are z equal to the 0, z equal to the pi. You see, this is a straightforward because you have to find the limit for the z, limit of integration. You have two numbers for the z. So your z is going to be between 0 and pi. Then they give you the y is equal to the pi. And then they give you the x equal to the 0 and the line x plus y equal to the 1. Okay, it's an easy domain because z is between 0 and 2 pi. Then you project it into the two-dimensional. The two-dimensional one is already given to you. You see, this is the line is x plus y equal to the 1, but they just restricted. In previous problem, y was 0. In this case, y is equal to the pi, which is going to be a horizontal line by itself. Okay, that's a different. But they ask you to evaluate this one. You want to evaluate triple integral on Q, and the function this time is x squared sine of z dv. Okay. Again, we have to work on the limit of integration first. So we look for the numbers that we've given for the z, information with the z, straightforward, z 0, 0 pi. So that give you quickly the restriction for the z. Okay, so we say note that I've already got the information for the z. So z is going to be between 0 and pi. This is z. Okay, now then you drop it down, projection into the two-dimensional. It's already given to when z equal to the 0. This is the two-dimensional one. So the projection of Q on the x, y plane in two-dimensional is going to be what? Is y equal to the pi, x equal to the 0, and x plus y equal to the 1. You look for the y, you see y is one of them is pi, and then you have x plus y equal to the 1. So what we do is we say the x plus y is equal to the 1. So I solve for y. Y would be 1 minus x. So that quickly give you the restriction for the y. Even you can graph it. You see so far what you have is going to be, so the y would be, this is it, y is y minus x, which is a line, and y equal to the pi if you like. So it would be between these two numbers, the y, but if you graph this line, it's not the intercepts. So what you have for your y is going to be, you see, if you put the x equal to the 0, y would be 1. So this is going to be 1. Okay, y would be equal to the 1. And if you put y equal to the, in this case, you see, if you put the, you have the y equal to the pi, you have to get this one first. Okay, pi is 3.14, so this is going to be y equal to the pi. Okay, this is going to be y equal to the pi. And the x and the y intercept of this line is going to be 1, 1. So if you connect them together, you see this is a situation that you're going to have. You see, this is going to be the line. This is the line y equal to the 1 minus x. It would intersect the y equal to the pi at this point. And if you replace y by pi, then your x would be what? You see, if you put y equal to the pi, so your x is going to be 1 minus pi. So this could give you 1 minus pi. So it's going to be your x. Now what's going to be the region in question now? The region in question is going to be between the line y equal to y minus x and y equal to the pi. So this is y equal to the pi, and this is going to be your line. So the region in question is here. And this is, of course, x equal to the 0. You know that the y-axis. So the region in question is this part. Okay. And you want to integrate it. You have to decide which part are going to be interested in. Okay, if you want to go with the x to the right to the left, if you go x to the right to the left, x is going to be between 1 minus pi and the 0, and you already got it here. Really, when you substitute, you will get it. And then in order to get the y, you just go up and down. That give you the result. See, up and down, up, down, up, down. So up and down is exactly what you have over here. So the down is y is 1 minus x, and the up is going to be pi. So the conclusion is going to be, for the limit of integration, your x is going to be between 1 minus pi and 0. And you have it here, you see. And your y is going to be, your y is below is 1 minus x, okay? Below is 1 minus x, and the top is pi. So these are the limits of integrations. Any question? So we look for the number for the z was clear, z between 0 and pi. But the number for the x and the y, this y equal to the pi is the one that we have to consider. Because in the previous problem, we're just taking the intercepts, that was the region. But since they intersect with the y to the pi, so the region is up here. So we just describe it. We know that the y is going to be between pi and 1 minus x. You already got it here. So that's a confirmation. And if you put the y equal to the pi, then you get the restriction for the x. But you better, graph it to make sure that which one is going to be below and which one is going to be above it. So we are ready to integrate it. Okay. So what's going to be the result of the integral? So this is the triple one that's given to you. And that's x squared sine of z dv. Now you know how to handle it. So it's going to be triple 1, 2, 3. Now, as we talk about it, you integrate respect to the z first, the z going from 0 to pi. That's a z. In between, you do the y, which is going to be 1 minus x to the pi. And at the end, you do the x. You do the x is going to be between, this is 1 minus x, this is 1 minus pi. 1 minus pi to the 0. And the function is x squared sine of the z. So this is going to be the dz, the dy, and the dx. That is how we're going to arrange this integral. Any question? So just pay attention, when you do a couple of examples, and you have a good feeling of picking this region, and they are going to be similar to each other. The integral is easy because you integrate respect to the z. The integral of a sine is just a negative cosine. You start to 0 to pi, give you a constant, then you continue taking those parts. Okay, so this is it. If you go with one part of the integration, so you have the 1 minus pi to the 0, you keep this one. Then you have the 1 minus x to the pi, you keep this one too. So you integrate this sine z, which is negative cosine, so to give you a negative x squared cosine of the z. Okay, cosine of the z, of course, going from 0 to pi. 0 to pi, and when you're done, you come back and you do the y and the x. Okay, if you put the pi and the 0, that give you kind of 2. So this is going to be integral from 1 to pi to 0. And this is 1 to x to pi. If you put the pi, so that give you negative x squared cosine of the pi. Okay, cosine of the pi minus negative x squared cosine of the 0. Then the dy dx. Now, cosine of the pi is a negative 1. Negative would be positive. Cosine of the 0 is 1. So you get a kind of a double negative. So this is going to be equal to, okay, so I write down here and just continue. It's going to be equal to the, I get 2x squared, but I want to explain it. So it's going to be 1 minus pi to 0. Okay, repeated 1 minus x to the pi. So we get the x squared plus x squared. Because there is a negative make it to the positive, and negative make it to the positive, and those are going to be just 1. So x squared plus x squared, and the dy dx is going to be 2x squared, and then we can continue integrate it. Okay, I'm going to go to the next page. Any question? So I get 2x squared, integrate respect to the y would be simply 2x squared y, and then continue. So this is it. It's going to be equal to, okay, you get your double integral. It's 1 minus pi to the 0, 1 minus x to the pi, but the function is 2x squared, dy dx. Now integrate it, that give you y, 2x squared y. So it's going to be 1 minus pi to 0. Okay, 2x squared y. So your y going from 1 minus x to the pi, and then you come back and you do the x, okay? So if you substitute in the first part, we get nothing. So it's a 1 minus pi to 0. In the first part, that give it 2x squared pi minus 2x squared times 1 minus x. Okay, 1 minus x and everything dx. You just simplify it and integrate it. So it's going to be 1 minus pi to 0, 2x squared pi, multiply inside the negative 2x squared plus 2x cubed. 2x cubed dx. Okay, easy. You cannot simplify it. You can factor out, if you like, but you keep it, and at the end you just do the factoring. So integrate it with respect to the x, so that give you 2x cubed pi divided by 3 integral of x squared. Again, the same thing here, 2x cubed divided by 3. And this is going to be 2x to the 4th divided by 4, going from 1 minus pi to 0. If you put the 0, we get nothing. If you put the pi, we can write it in terms of pi, or just use your calculator. Okay, so it's going to be equal to the 0 minus. If you put the pi, so that gives it 2 times 1 minus pi. 1 minus pi cubed times pi. That's the first part, minus 2 times 1 minus pi cubed over 3. And the 2 times 1 minus pi to the 4th over 4. Okay, you can use your calculator. But if you want to do the algebra, you better pull out 1 minus pi cube and then simplify it. So this is going to be the case. Okay, it's equal to, I apply this negative sign first, and I pull out the 1 minus pi 2 times, so it's going to be minus I pull out the 2 times 1 minus pi. You know, you can use your calculator, but this is the way I like to do it. I pull out the negative here. So the leftover here is going to be pi third. Okay, that give me the pi third. And the leftover here is going to be just 1/3. Because I've already pulled out the 2. Okay, and the last part here is going to be minus 2 times 1 minus pi. You know, you can use your calculator, but if you want to stay with this notation, you need to find the common denominator and just take care of it. Okay, that was a 3, 3. Yeah, I could simplify this too. So the common denominator would be 6, 2 times 1 minus pi cubed. The common denominator would be 6. So that gave me 2 pi plus 2 and minus 3 times 1 minus pi. So it's going to be negative 2 times 1 minus pi cubed. And the inside is 2 pi plus 2 minus 3 plus 3 pi over 6. Okay. Seems to be all right. You know, I have a better format, but you have to check it, you know, with your calculator. I didn't miss a negative sign. When I pull out the negative sign here, so I apply this negative sign. Okay, that's I apply the negative sign, so this must be negative, this must be positive, and this must be negative. You know, it's correct. But anyway, you can use your calculator. It's going to be 5 pi minus 1 over 6. So that give you, that give you the result of the integrations. Okay. You don't think I think factor out of the final part? You can simplify it. Okay, that's one. So what I did, I tried to simplify it. So that's why I pull out the, okay. Yeah, you are right. I pull out the 2, okay, 2 times 1 minus pi cubed. So this must be done. You are right. Okay, because I pull out the 2 here. So I have to keep the 4 to get to the numbers. But anyway, try it again to see. It was nice one when I did it. It was, I think it must be this one. 1 minus pi all to the 4th over 6. That should be noted, but you can check it to see what is going to be the result. Okay, so that gives you the idea of the triple integrals, the one we are going to have. In order to be able to do a kind of a symmetrical form related to the, ellipsoid sphere, which is going to be very important, we need to go through the cylindrical coordinate and the spherical coordinate. So on Monday, I do the cylindrical coordinate, I change the triple integral into the cylindrical form, and on Tuesday, I change it into the spherical coordinate and I do the job. And on Wednesday, I do the substitution method. Okay, a kind of U substitution or substitution method for the double integral. And then we are done with this chapter, and we can give you the test on time. And test 3 is very important. Whatever you do on test 3 is going to be repeated on the final. Okay, because we need just a couple of more questions for the final. So take that one very seriously, even if you already got nice point on test 1 and test 2. Make sure don't miss the test 3. Take it, even if you want to drop it. Take it because in the week time, you are going to see it on the final. Okay, so that's my suggestion to get an excellent grade on this test, because it's going to be, you get 3 new problems for the final besides test 3. And those problems are easy. But the challenging one is this part that we have, this cylindrical coordinate and the spherical one. Otherwise, we'd be fine. Okay, any question? No.
May I,
Yes.
sorry. May I ask a question about this problem? I don't know if I'm mistaken, but where you have the 0 minus the rest of the input of the integral,
Mm-hmm.
if you distribute the negative, it becomes negative, positive, negative.
Mm-hmm.
And if you pull out the negative again once you factor, wouldn't it be the opposite?
I can do it. You see that this is the one I usually get, 1 minus pi. Let me just check what I missed. You see this is a negative sign. I put it out, okay? I put it out maybe quickly or early. So this is, so I keep the negative, okay? I kept the negative over here, so I should keep only, take out 1 minus pi cube only, okay? So this must be positive, this must be negative, you are right. This must be positive, okay? So we continue, and this is going to be positive. This would be negative, okay? And this would be positive, okay? So we go on 2 pi. Now what we have, 2 pi, this is negative. Okay, so this would be positive. This would be negative. Okay, now what we have here now, we get the one that I'm interested in. We get the 2 pi minus 3 pi, which is going to be negative pi. Okay, and you have a negative 2 plus 3, which is going to be a positive 1. Okay, so I have the 1 minus pi here and the 1 minus pi here, which make it to the 1 minus pi to the 4th. Okay, 1 minus pi to the 4th, and I should have the 2 and the 3. So this should be correct. I think that's going to be the case. Yes. So that would be, yeah, I missed the, I made a mistake here when I did the sign. Okay, everybody agree over here? So you see, if you just, I did this one early. So what I did, I kept the negative sign. I kept the negative sign. So I just pull out 2 times 1 minus pi cube from the inside. So the sign inside must stay the same. Positive, negative, positive. Okay, positive, negative, positive, positive, negative, positive. So that would give us a, okay, this factor, let's see here, 1 minus pi cube and the 1 minus pi. So make it to the 1 minus pi to the, okay, 1 minus pi to the 4th. And the bottom one, I believe that these two would be simplified because I have the 2 outside. So that gives 1 minus pi to the 4th over 3. I believe that is going to be, yes, Daniel, that's correct. So that's the correct answer, 1 minus pi to the 4th over 3. Okay, any question? So, I didn't like to use calculator. I love to do this type of operation, but if it's going to be on the test, you can use your calculator here and give us, give us the numbers. But it's nice, a nice answer. I knew that it should be something to know to simplify. Okay, so we have time, so we go to that practice one. Let's try a couple of those problems because that practice quiz is important, and we do all the problems on that practice one tomorrow for you, and we try to give you all of them, all different types. We are not going to give you a triple integral for the quiz, but you will see it on the next test. Okay, any question? So get to know the triple integral, to have a good feeling about it. The way we do it, quickly be projected into the XY coordinate. As soon as we get the XY coordinate, it's the same old problem of the double integral. Okay, let's see if we can do a couple of those problems, because that would be, I remember that that takes quite a while to be able to do it. Okay, so let me bring it up for myself and just checking. So what we do, so this is going to be practice quiz number 3. Keep all these solutions because that's part of your final review. Okay, and I will post, you already got the final review, you can have a look. You will see them again. So that would be practice. Okay, practice quiz. Number 3. Okay, so we give you one straightforward integral, the double integral to evaluate for us. Okay, in this problem, everything is nicely done. I just want to check, make sure I have the correct one here. Okay, so this is practice quiz number 3. Yes, we give you question number 1 is just straightforward. Just to find it, we give you 1, everything would be given. And the limit of integration, you don't have to find it, okay? So number 1, we give you 1. That's first topic that you have to know. Evaluate. When we're going to be on the final, we make this one into 2. One with a double integral, the other one triple. We want to evaluate each integral. Each double integral. Write down, the first one is easy, but we can try it. So part 1. So you don't have to get the region of integration. Everything is nicely done. 1 to 2, and this is 0 to 4. Okay, 0 to 4, and the function is just a polynomial to warm up if you like. But don't expect this kind of polynomial for this one. We are going to be interested in the kind of exponential one or trigonometric one. Let me give you something that's going to be easily done. Okay. Now, you know that this is a rectangular one, just integrate respect to the x first and the y. So this is it. I'm going to call it I, and I continue. Now, you know it, we do it quickly. So it's going to be integral 1 to 2. We integrate this by respect to the x. So that gives us x cubed over 3. Okay, minus 2xy squared plus x. Then you have to go from 0 to 4. And when you're done, we come back and take respect to the y. Okay, so that would be a kind of straight forward. Just going back to see you. Yes, that's it. Okay, nothing to simplify. So substitute. We substitute the 4. So it's going to be 1 to 2. So that gives you 4 cubed divided by 3. It's going to be 2 times 4 times y squared plus 4. And if you put the 0, everything would be 0. Okay, and then you integrate respect to the y. So this is going to be integral from 1 to 2. 4 cubed, 16, 64. So 64 over 3 minus 8y squared. And we get a plus 4. And integrating respect to the y. Okay, you can simplify those two numbers. So 64 over 3 minus 4. And so common denominator would be 3. And so it's going to be 12 plus 64. Okay, 76 minus 8y squared. Okay, dy. I just add the 4 to the 64 third plus 4. And now you integrate respect to the y, and then you just substitute, and then you're done. So it's a 76 over 3y minus 8y cubed over 3. And you have to evaluate it from 1 to 2. Okay, so it's not a big deal for this problem, really. You substitute the 2, and it's going to be 76 over 3 times 2 minus 2 cubed over 3. And when you put the 1, that gives you 76 third minus 8 third. Okay, so just put these numbers together and just find the result. Okay, 2 times 6, 12, 14, 15 third. And this would be 64 over 3 minus 76 third and plus 8 third. Okay, so this is going to be easy. 152 and 8, that give you 160. So you're going 160 third, and this is going to be minus. You put these two together, Okay, that give you 140 over 3. So the final answer is going to be 20 over 3. You get the number. Okay, that's it. That's a warm-up to get this group. Any question? So that's part 1, polynomial type. But the part 2 is the one that you have to be patient, okay, to get to read. And again, there are going to be the limit of integration. Everything will be given to you. Are you ready? So let's do part B to have this done again. So that's going to be part B. You want to integrate this one. Okay, evaluate 0 to 6. Okay, 0 to 6, 0 to 10. 0 to 10 square root of x plus y, the dx dy. Again, limit of integrations, everything nicely given. We want to integrate respect to the x. You know that you have to change the radical, rewrite it. So the integral is going to be 0 to 6. Okay, 0 to 10. So we have x plus y to the 1/2 dx dy. Okay, so this is easy to integrate respect to the x. You know that for the u substitution, the u prime is 1. So you don't have to do anything. You just raise it to the 1/2. Okay, and just you'll be fine. So it's going to be 0 to 6. So that would be x plus y to the 3/2 over the 3/2. Okay, then going x go from 0 to 10. And when you're done, you take the integral respect to the y. Because the u prime is 1, you know, when you differentiate respect to the x, so we don't have to worry about it. So use the reciprocal of that number. So that gives you 2/3. Okay, 2/3 x plus y to the 3/2. Okay, this is going to be the one, and then you evaluate it from x going from 0 to 10. And when you're done, you integrate it respect to the y. You can bring out the 2/3, put it out, and then substitute. It's going to be 0 to 6. You substitute x equal to 10 first. So that gives you 10 plus y to the 3/2 minus, you replace x by 0. So it's going to be minus 0. I write it down so you know what's going on. 3/2. Okay, and then dy. You cannot simplify it, so this is going to be just a 2/3. Okay, it's going to be 2/3 0 to 6, and you have the 10 plus y to the 3/2, and that would be simply y to the 3/2. Okay, and then integrating respect to the y. Again, for the u substitution, because the u prime would be 1, so nothing to worry about. Just apply the power rule again. So that gives you 2/3. The power rule gives you 10 plus y. Okay, 10 plus y to the 5/2 divided by the 5/2. Okay, and this one is going to be y to the 5/2 divided by the 5/2, and then y going from 0 to 6. Okay, again, you are not going to get anything nice. Use the reciprocal of these numbers. And so that gave you the 2/3. Reciprocal of the 5/2 would be 2/5. You can pull it out. Okay, multiply by this, and then get those. Okay, so the inside is like 10 plus y to the 5/2 minus y to the 5/2 to be evaluated from 0 to 6. So if you just substitute, so that give you 4 over 15. Okay, 4/15 outside. And if you put these numbers, okay, so that give you 10 plus 6 to the 5/2 minus 6 to the 5/2. And if you put the 0 minus, okay, if you put the 0, you get 1 here, 10 to the 5/2. Okay, for this last part, we accept if you use calculator, but you have to show your work here, okay? But for these parts, the substitution one, you can use your calculator and we accept it. If you don't use your calculator, just write the answer as is, we accept it again, because this is going to be 16 to the 5/2. And that simply is going to be 6 to the 5/2 and minus 10 to the 5/2. Okay, you can use your calculator if you like, otherwise this is the best we can do. And we usually use calculator as soon as we get to this part. And again, we accept it. Okay, if you do it. So that would be the part B. Any question? Again, as you can see, you got to be patient. They are not difficult, but sometimes it's messy. But don't worry. But the one that you will see on the test, they are nice. You know, this can be done. So that's part B. I get time to do the part C as well, because there's a point I want to explain the part B. Part C. Okay. So this is going to be part B. And the part C, this version of the kind of a natural log function that you need. You want to integrate this one, 2 to the 5th. Okay, 4 to the 5th. Okay, 2 to the 5th, 4 to the 5th, and this is going to be xy plus yx. And it's a dx dy. You have a similar one in your book, but I just want to check it. Okay, don't try to do anything to this. Leave it as is. Okay, we have to integrate respect to the x first. Okay, so when you want to integrate respect to the x, this would be just x. It's like x times 1 over y. So it's going to be x squared over 2. This would be like 1 over x, which is going to be, can be done by the ln x. Okay, so the first part of the integration, I'm going to call it I, is going to be, you keep the outside 2 to the 5th. We integrate respect to the x. As we talk about it, this would be x squared over 2, which is 2y. And integral of 1 over x would be ln x, but you have the y, ln of the absolute value of x. Okay, and the x going from 4 to 5th. And when we're done, we get the dy. Any question? So again, be careful about this. Then you have to substitute the 5 for the x, 5 and the 4. So that gives you quite a lot of the ln values, but it's fine. So this is it. So we keep the 2 to the 5th. Then we substitute for the x, we substitute the 5, so that gives 5 squared over 2y plus y ln of 5. Then it's going to be minus, if we put the 4, so that gives 4 squared over 2y, and that is going to be y ln 4. Okay, everything is going to be dy. Okay, so you know it's going to be 2 to the 5th. So 5 squared 25 over 2y. So it's going to be y ln 5. And this is going to be minus 16 over 2, 16 over 2y, and the y ln 4 as is. Okay, you know, this is the case. Rather unusual, but you know, it's happened. So the thing that we can do is 25 over 2y and the 16. So 25 minus 16, that gives you 9. So we can rewrite it as a 2 to 5. 2 to the 5, 9 over 2y. And over here, you know, we can use your calculator or just write it down as is. Not a big deal to simplify it at the end. ln 5 minus, okay, plus y ln 4. Okay, now integrate respect to the y. It's a 9/2 of the 1 over y. 1 over y would be ln y. You don't need the absolute value because the interval is it's a positive. So this would be 9/2 of the ln y. And of course, this is going to be y squared. Okay, y squared ln 5 over 2. And this is going to be y squared ln 4 over 2. That's going to be a value from 2 to 4. Again, you need calculator, otherwise you just substitute to get the result for yourself, okay? Again, this is, you have a similar one in your book. I just want to show you how to do it, but otherwise, it's just you just substitute and just find it with your calculator. ln 4 plus, this is going to be 4 ln 5 over 2, and this is going to be 4 ln 4 over 2, and then you repeat it for the, okay, you repeat it for the 2. So it's going to be 4 ln 5 over 2, and plus 4 ln 4 over 2. Okay, so just use your calculator to get the result. Just to show you that, these are going to be the type, but just don't worry, if you see it, you can do it. Nothing to worry about. So that would be number 1. I continue doing the rest tomorrow. So the number 2 are going to be a good one. The first one, integral of x y e to the y dA is the one. So we continue and we finish all of them tomorrow. Okay, any question? So no question from the triple integral, remember. No question from the triple integral. So the surface area and the double integral. So